So now let's talk about locks. We understand why you need locks because we saw in the previous example that we need some way to keep two different processors from both using the same data at the same time. So, what is a lock? A lock is just a variable that protects data. You have to acquire the lock or get the lock before you can access the data. And when you have the lock, no one else is allowed to access it. So when you have a lock, it gives you exclusive access to the data. When you're done, you release the lock and you give it up so other people or other processors can access it. So let's see how we change our code. Here's our online order. Here's the code we had before. Now we're going to change it so that we first check if we can get the lock. So what this does here is it says try to get the lock, and if I do get the lock, then go ahead and execute the code. If I don't, just wait. We do the same thing with our withdraw code. We check to see if we can get the lock. Now what happens here is only one processor can have a lock at the same time, so that means only the order, the online order, or with the withdrawal are going to get access to the data at the same time, get access to the data. So they get exclusive access, one or the other, and this will prevent them from corrupting each other's data. So let's take a look at this. Now in our DRAM here we've got both our balance and our lock variable, and let's go ahead and execute it. So process 1 goes and tries to get the lock. It sees the lock value is 0, so it says, now I can get the lock. It sets it to 1. Now it's going to go ahead and execute. It's going to load the balance. The balance is 510, and it can go ahead and process. Now, in the same cycle, we have process 2 come in and try and do the withdrawal. Now, the first thing it does now is it checks if it can get the lock. Well, the lock value is 1. That means somebody else has the lock. So now processor 2 has to wait because the lock is busy. So what happens next? So we go through and we're going to continue in processor 1. It's going to do its computation. The DRAM value stays the same, but now processor 2 is going to check the lock again. Is it free now? Well, it gets the value it's not free now, so it has to wait again. Processor 1 over here is going to go ahead and store its new updated value. So now we have 10 in the DRAM, and the lock is still 1, and so processor 2 is going to check again, and it sees the lock is still busy. Finally, processor 1 is going to go ahead and finish, and it's going to unlock the lock. So when it unlocks the lock, it's going to write a 0 into the lock. We've still got 10 in the DRAM. So we've got a 0 in the lock. Now at this point, when processor 2 goes to see if it can access the lock, it's going to see this 0 and see that the lock is free, so it can go ahead and execute. Now it's going to go ahead and take the lock by setting it to a 1, and now it can begin to execute. So it loads the balance, and it gets the balance, which is 10. It checks to see if the balance is greater than 200. It's not, so it doesn't update it, and it goes ahead and fails. So it tells you you can't do the withdrawal. So this worked the way we expect it to. And then finally, when it's all done, it's going to have to go in and unlock the lock itself so that other transactions can proceed. So, what did processor 2 do while it was waiting for the lock? Well, it just kept checking the lock value. So it was 100% busy doing nothing but reading the lock. You can see here this whole time it's just read lock, read lock, read lock, read lock, trying to see if the lock is available. So this is really inefficient. And what you do in a real lock application is you try reading a bunch of times, then you decide it's going to take a long time, so you'd give up. You'd have this exponential back off. You'd try waiting 100 cycles and 1,000 cycles and come back. This is the same thing that Ethernet does with the collision. You have this exponential back off to wait for longer and longer periods of time rather than trying to check constantly. So how do we implement a lock? Well, as you saw in that example, a lock is just a regular memory location. If it's 0, it means nobody has the lock, and if it's 1, it means somebody else has it. So to get a lock, we need to try reading it, seeing if it's 0, and if it is 0, writing a 1 to it to say we have it. So here's our code. We have a little thing which we try to get the lock. We're going to go first and we're going to read the lock, so we're going to load the lock value into R1. If R1 is 0, then we can go ahead and take the lock. If it's not 0, we're going to keep trying again. Keep trying until we can get the lock. Now if it is 0, that means nobody else has the lock. We're going to jump down to take the lock, or we're going to put 1 into the lock to say we have it. So this is what we need to do, but there's a problem. What if someone interrupts us? So between the time here, when we load the lock and when we write a 1 into it, other processors could change the value of the lock, and then it wouldn't be clear who had the lock. So in order to make locks work, we need to modify the processor. We need to be able to do a read, check, and write with no interruptions. That is, we need one instruction that's both going to read the value that was previously in the lock and write in a new value and make sure that nothing can get in between those two read and write. The way this is typically done is with an atomic swap. So an atomic swap is going to put a 1 into the lock location and read back the results in one instruction. So if we get back a 0 from the atomic swap, that means there was a 0 in the lock before and no one had it, and now we do have it because we put a 1 into it. However, if we get back a 1, that means someone else had put a 1 into the lock. Someone else had it, so we swapped in another 1, so the lock still stays 1, but we know that we didn't get the lock and have to try again. So the code for doing the atomic swap is we have a 1 in register 1, and to try to get the lock, we swap our 1 in the lock. So this is going to put 1 into the lock and put whatever value from the lock into register 1, and it's not going to allow anything to interrupt that read and write. Then we check and see what the results were. If we got back a 0, that means there was a 0 in the lock before and we have the lock. Otherwise, we keep trying again. So the key thing to remember here is a swap does both a read and write, and we need to do this in hardware so that nothing can interrupt it. Because remember, if we can't guarantee that instructions come between here, we have the same synchronization problem that we had with the bank account example. So to summarize synchronization, we need to make sure that when we have multiple processors running, that the processors don't use outdated data. If we modify data on one processor that's going to be shared, we need to use a lock. We need to first check and see if the data is locked, and if so, wait for it to be unlocked. Then we lock the data when we start, we do our update, write the data back. Once we've done that, we unlock the data so that other processors can access it. If we use this correctly, it prevents what are known as data races. Data races are where data gets corrupted because different processors have different versions of the data. And I should point out that using locks correctly is hard. Let's take a look at an example of that. So there's a famous machine called the Therac 25, which is a radiation therapy machine used in the 1980s. This machine had a problem with locks. It had a problem with the locks between the equipment control, that is the circuits that controlled the radiation device, and the operator control, that is where the doctor put in how much radiation should be delivered. And these weren't synchronized correctly. So what ended up happening was you got the wrong information to the doctor and the equipment. So the doctor would program a particular radiation level, but the equipment would give a different level. The results were there were at least 6 people who got 100 times as much radiation as they were supposed to. So a very serious result of not having correct synchronization. Another example is the Northeast blackout in the United States in 2003. Here they had improper use of locks when handling simultaneous failures. So this is very close to the banking example. What they had is when they detected multiple failures on the power lines, those failures overrode each other and corrupted the data. They didn't correctly lock around reporting multiple failures. And this blocked the alarm indications and made for a much, much larger power failure. In all, 55 million people lost electricity because they failed to do the correct synchronization for handling these failures. So, what does a lock lock? Well, a lock doesn't actually lock anything. A lock is just an indicator to the program that other processors should not change whatever that lock is protecting. It's up to the program to pay attention to the lock and know which data has to be locked or which data the lock applies to. Remember, a lock is just a variable. The trick to using the lock is to make sure that you look at the right lock variable when you're changing the right data. What would happen if you had 100 processors all trying to get the same lock? Well, 99 of the processors would be waiting all the time. So only one of the processors gets the lock, and all 99 other processors are going to sit there trying to get the lock. This is called lock contention, and it's one of the main reasons it's hard to make parallel programs go really fast. If you have to share data, you have to lock like this, and that can slow things down if multiple processors are all trying to get the lock at the same time.